Hello, welcome. Today we're going to be looking at dynamic systems and control. How do you start controlling a system? We said that we do process control because the systems are dynamic. Many things change in a system. It's a transit process. Every process of production that you're having, things are always changing. When you continue heating a system, the temperature will continue to increase, and when you cool it, it will decrease. So things are changing. Variables like temperature, pressure, are always changing. Amounts of material that are going inside the system and the ones going out are always changing. So how do you control such systems? How do you know where to install valves, where to install sensors? How do you know how to go about controlling a system that has variables that changes? And I would say that a system is a part of a process or is a procedure for a process to produce something or to transfer something from one form to another, from one substance to the other. So this system actually is where you're studying, or say your production. Let's say this is your production plant or production line or a process in your production plant. You understand? So once you mark it out with a boundary as a system, every other thing is known as the universe or the surrounding of the system. Understand? So let's say you get to a refinery plant and you just get to the tower, the rectification tower, the distillation, the fractional distillation tower. If you are considering that fractional distillation tower as a system, then every other thing is the universe. You understand? Because that's the only way you can control. You need to be able to define your system. If you're controlling the whole plant, you know you're controlling the whole plant. But it's always good you start from smaller one. So if you're considering a particular point in a production plant, you call it system. Then any other thing around it is the environment. So this very system is always having input coming from the environment and output going out into the environment from the system. You understand? So these inputs and outputs, there are things like energy and materials that are moving, like the crude oil moving into the distillation column, and the output, the refined products coming out. You understand? Or any form of energy, the heat that you're supplying to help the rectification. You understand? So all those things are known as variables or inputs and outputs going into the system and going out. But every other thing that is not the rectification tower is known as universe. But the rectification tower itself that you're looking at and you want to control is known as the system. So any part of the universe that you want to do control, you want to study, is known as the system. You understand? And the system is always separated from the environment by the boundary. You can see the boundary. So this is the system making up of a process, a sensor. This sensor is not connected very well. So I'm supposed to connect this, get this information, text the information to the controller to enable the control. So when you look at this system very well, you see that this is a process, very, very important. You need to understand how this system works. This is the process, this is the system. The space that is under this boundary, this is the system boundary. So there is always inputs like mass. Let's say that this is a petroleum refining system. You have to supply things like the crude oil. You have to supply the crude oil. If this is a refining plant, you have to supply inputs like the crude oil. You have to supply heat energy. You understand? You have to supply, let's say you're supplying crude oil here and you're supplying heat or other things that you need, your catalyst, everything that you need for this process to go through. So after the processing, you get your outputs like your PMS, your kerosene and other things. You understand? Now when you're supplying this, you have a set point of what you want to come out here. You understand? Let's say you want concentration of so and so of PMS to be coming out, of methane to be coming out, and you check it using the sensor. All of a sudden, it's not giving you this concentration that you need. So what happens is that this sensor senses this change. That means that this thing has gone out of set point because you already set up the percentage of methane that you want to be contained in the fluid that is coming out. you have a set point. So let's say that set point is not what you are saying. What do? This sensor picks what is coming out. You understand? It gets the difference between what the set point is and what is actually coming out. So it sends this to the controller. This controller will now, instead of allowing normal crude oil to come in, it may now allow crude oil, diluted crude oil that is not the same as the normal one, to come in order to have a steady process that will produce the real set point that you have. You understand? But if this is normal, if it does not notice any changes in the set point of maybe one of the concentrations of the effluent, the thing continues to work normally. The crude will go in, gets refined, come out, go in, gets refined, come out. But anytime it checks it and the concentration is not what it wants, it picks those difference and sends it to the controller. The controller will now know what it will collect in order to fix this back to the normal point of control, which is known as the set point. So that is what the sensor actually does. It checks the output, see whether it's of the quality that you want. If it is of the quality that you want, it does not send any message to the controller. Everything continues from. But if it checks it and it changes, it will send out changes to the controller so that the controller will take the appropriate action using the final element. You understand? After it must have manipulated this variable that is coming in, instead of it coming in normally, it will manipulate it so that this effluent will get back to the set point. The output will get back to the set point, and that is the whole essence of control. You control using sensor. Using these sensors, you use valves and other things to get the message here, send it to the controller. The controller does things using the final element, manipulates what is going in so that you get what you actually want. You understand? So this is the output coming out. You can have other outputs, you can have other inputs. So set point is very, very important. Values here are set as set points so that the sensor reads. Once it's not the set point, it sends the information to the controller to do something about it. You understand? So these input and output flows are actually flows of matter and energy. Make sure you note that matter like crude oil, energy like heat and all those things. So those are the things that are input and output variables. Now, having known that this is how a control system works, how are you able to calculate these set points? You understand that this sensor will take to the controller. How do you know where to place the controllers? How do you know that? For you to know that, you need to do what we call modeling. You need to do what we call mathematical modeling. And mathematical modeling simply means looking at a system and writing equations that you can use in describing such systems. So when you look at a system, you know the variables of the system, you know the inputs and outputs. Use those variables and develop a model, a mathematical model, a mathematical equation that you can look at, so that if you want to build a control, you can be using the values from that equation to build a control. So in describing a dynamic system by mathematical models, how do you go about describing a system by mathematical model? Number one thing is that you use linear approximations to define a system into mathematical method. You use linear approximations to equations describing the system in order for you to get solutions. So if you can write a mathematical representation of input, what is going on, and the output, you can be able to solve out those variables, get what the input should be, what the output should be, so that you can use them in building your control. Now you also have to resolve some of the structures inside, all these structures that are inside the system. You need to resolve them. You need to do what? Resolve some of the structures inside the system boundary to distinguish between a process and additional equipment used to control the process. Very, very important. This is the process, whereas all these ones are additional equipment that you use in controlling the process. So you should be able to always identify the process and distinguish it from all these other controls that you are using to control the process. So to do this, we use what we call a feedback control. You always use what we call a feedback control that can be further divided into cascading type and the feed-forward arrangement, which we are going to explain in details in subsequent classes. Now, modeling and solution technique includes, if you want to model a system or a dynamic system and find solutions to them, just like we say, for you to do this, for you to start any control, you need to do what? Use a linear approximation to model this equation in order to find the solution. So this modeling and solution technique include number one, you need to do what we call linearization of equation. Like I said, you have to use linear approximation to define every system. There's always a mathematical equation for how the system works, where you equate the independent variables to the dependent, where you equate the independent variables to the dependent variable using a model. So you need to make sure that you get it into linearized form using Taylor series approximation to make it easier for you to solve. Now you need to do what we call arranging the equations in standard form. You arrange your equation, the linear equations that you've gotten, arrange them in standard form, because you're going to be getting some polynomial equation. Always try to linearize and arrange in standard form. Use basic elements like first order lag and dead time to solve complex equations in order for you to arrange them in standard form. Use Laplace transforms, very, very important. Also use block diagrams and Laplace domain transfer functions to solve other equations that you derive from this. Also use time domain response, very, very important. When you are done with that, summarize the response in sinusoidal form to derive a frequency domain. Then finally, you now need to do what we call extensive consideration for stability limit. You need to do what we call extensive consideration for stability limit. Once you are doing the stability analysis, then you know that you are trying to control the system. So very, very important, you need to understand the system that you want to control. Now you need to make mathematical model of this very system that you want to control by describing the variables, the inputs and attributes in form of mathematical equation. Linearize such equations, identify and distinguish between the real process and the control equipment. Make the mathematical model and solution of this very system that you're studying in order to do the control. And for you to make this mathematical modeling and solution of this system, you need to find linearized equation for the mathematical model using Taylor series approximation. Arrange these equations in standard form. Use basic elements like the first order lag and the dead time. Use Laplace transform and use block diagrams and Laplace domain transfer functions and time domain response, and also summarize your response in sinusoidal frequency domain, and then do your extensive consideration of stability limits in order for you to ensure your control. So in subsequent classes, we are going to be studying this stability unit and know how to use it to ensure control in the chemical process or in the system. Thank you. If you like this video, click on the subscribe button, share it, help us in any way you can. Thank you and God bless you. Great.